everyone. In this video, we're going to talk a little bit more about why angle side side can be difficult, why it's not our favorite. So thanks to Seth Braver's pre-calculus book, this has been dubbed the ambiguous ass, ASS. So there are, I guess, 4 different things that can happen. A couple of them are kind of weird and a couple of them are not that crazy. They're sort of what we'd be expecting. So I just want to walk through so that you can see all the different things that can happen. Okay, so I'm going to fix 2 things. One is angle A is 30 degrees, and the other is that side length B, so that's not the side opposite angle A, it's one of the adjacent sides. Side length B is 1. And then I'm going to play around with the length of side little a, which will be opposite angle big A, and see what happens. Okay, so in number 1, I have side length A equals 0.3. So I have my 30-degree angle here. I know this side length of 1 is sticking out. It could be the top or the bottom. I just like to draw it sticking out the top. So here's the base of my triangle. I don't know how long it is. I just know it sits on this horizontal line. And I'm getting this side length of 0.3 to try and connect back down to where the base has to be. This 30-degree angle has to be here, so the base has to stick out in that direction. So if we want to try law of sines on this, let's just say, I don't know what it looks like, but maybe it's kind of close to being a right triangle. We can try this. And law of sines would say, okay, you've got a known pair, 30 degrees and 0.3 side length. And you've got one other known side, so you should be able to pair that with this angle. That was B, so we'll call this beta, and solve for angle beta. So this would be sine alpha over A is, oh, I guess I called it big A. Sine A over A, so we'll just call this big B, equals sine B over B. And this is sort of tradition just to make it easier for us to keep track of what's across from what. You'll see angles labeled big A, big B, big C, for example, and then the opposite sides would be little a, little b, little c. Or you'll see the Greek alpha, beta, gamma, and the opposite sides would be A, B, C. Okay, so sine A over A. We know that big A is 30 degrees, so sine of 30 degrees, and little a is 0.3, should equal sine B over 1. So sine B is equal to sine of 30 degrees over 0.3. And I actually made this one kind of easy on us in that sine of 30 degrees is like our pi over 6. So sine is 1/2. So if you want, you can even use that. This is 1/2 right here. Otherwise, we're solving for B, so we're going to take the inverse sign. So I'm going to say that B is equal to inverse sine of 1/2 over 0.3. And I'm going to ask my calculator, what do I get when I take the inverse sine of 0.5 over 0.3? And it gives me an error, a domain error. So let's investigate a little bit further. If we take this 0.5 divided by 0.3, we're getting 1 2/3. So B is the inverse sine of 1 2/3, 5/3. So the reason this is giving me an error is because it's impossible for sine to be bigger than 1. If we're thinking unit circle, the biggest y value you can get is 1. If we're thinking triangles, this is supposed to be opposite over hypotenuse, and hypotenuse should always be the longest side, so this should be impossible. So actually, my calculator is doing a good job telling me that this doesn't work. So it's saying this is undefined. Okay, so the question is, why is this undefined? And the answer is, when we did this, sine of 30 degrees equals 1/2, what we figured out was that if we really do make this a right triangle, then the height of the triangle will be 0.5. And all I've given us is a length of 0.3 to try and get down to the bottom. So I have this length roughly like this, 0.3 long, and it's trying to hit the bottom. And granted, I don't know which direction it's pointing. It could swing back and forth, But no matter which direction I pointed, if I can only go 0.3 units from this top corner, I'm not going to be able to hit the base of the triangle. Sorry for the wobbles. So what law of sines is trying to tell me is that I have no triangle. Okay, so basically what happens is this 0.5 is the height of our triangle. So regardless of how long or which direction that side sticks in, from the bottom here, the height of this triangle, if this is the top corner, is going to be 0.5. So if our A value is smaller than the height of the triangle, then we can conclude there's no triangle. That doesn't actually create a triangle. So with a lot of the trios of information we get for law of sines, you're not going to ever say that's not a triangle. It's enough information to determine a triangle, and you'll never have this weird problem. But with the angle side, that is the one where, because we only know this one bottom angle and this side could point in any direction, if you choose the wrong length, you might not get a triangle at all. Okay, so let's look at the next one. The next one is if A is exactly 0.5, and actually based on the work we already did, we figured out that exactly 0.5 is the height of the right triangle. So we kind of have advanced knowledge, but we can say what law of sines would do about that. So if we started off, let's see, what are we going to do here? So pretending we don't already know that's a right angle, if we call this B again, we would say we have our sine 30 degrees over 0.5, and that should equal our sine B over 1, which means sine 30 degrees was 1/2, so 1/2 over 1/2 is equal to sine B, which means that B is equal to the inverse sine of 1. And I don't need a calculator to tell me that. If I think unit circle, when is my y value 1? My y value is 1 right at the top of the circle, which is pi over 2 radians, or 90 degrees. So law of sines will work on a right triangle, but it's not necessary. If you already know it's a right triangle, then you already know that bottom angle is, in this case, the bottom angle is 90 and the top angle is 60. So you can figure that out without law of sines if you've got a little bit of extra knowledge about the triangle. Okay, so in general, sometimes it won't be so obvious because we won't have special values. If A is equal to the height of the triangle, then we can conclude that it's a right triangle. So we get one right triangle. So kind of special, but nothing too crazy. We get a triangle. Law of sines will tell us what we want to know about the triangle. That's great. It just happens that that triangle is a right triangle. Okay, so let's look at possibility number 3. Possibility number 3 is not supposed to say A is equal to 0.3. It's supposed to say A is equal to 0.7. And in fact, the last one I want to be, let's make it 1.3. That would be fine. Okay, so if A is equal to 0.7, we know that the height of this triangle is 0.5. And now I have the side opposite the 30-degree angle is actually just a little bit longer than that. So I'm thinking that that's probably going to kick it out this way. Okay. Here's the problem. That might be what I'm thinking, but that's not the only option. That side length could kick out in this direction, or it could kick back in the opposite direction. So it could really go either way, which means there are 2 possible triangles. So there's the smaller triangle, and then there's the bigger triangle. And this is the ambiguous part. 2 possible triangles could be described by the information that I was given in this problem. So let's just see what law of sines does with it. If I say sine of 30 degrees over 0.7 is equal to sine of B over 1, and B is hopefully going to be one of those 2 angles, then I get 1/2 over 0.7 equals sine B. And B should be the inverse sine of 1/2 over 0.7. Inverse sine, there we go. Okay, so if I take the inverse sine of 0.5 over 0.7, I get a roughly 45.58 degrees. Okay, so looking back at my picture, I have two triangles. The pink triangle, this would be angle B, and the purple triangle, this would be angle B. So we'll call this B1 and B2. And this has definitely given me B1. In fact, law of sines would always give you B1, this outer angle. The reason for that is when you take the inverse sine, it's always going to give you an angle between negative pi over 2 and pi over 2, which is negative 90 and 90. And in the case of triangles, we're not interested in negatives, so let's just say it this way. Inverse sine, when you're looking at a triangle, is always going to give you an angle between 0 and 90. Always. It's never going to give you an obtuse angle that's bigger than 90, like B2. So law of sines gives us one. The question is, how do we get the other one? And the answer is, if you're paying careful attention to this picture, I said there were two triangles, and there are two triangles that fit this information, but there's also a third triangle that I can use, even though it's not one that fits the description in the problem. There's this little triangle in here that has side lengths 0.7 and 0.7. And what's special about this triangle is that it's an isosceles triangle. So if this angle over here is B1, then this angle over here is also B1. So we have this really nice symmetry. And again, that happens because both of these side lengths are 0.7. This is from the top kicking out 0.7 or kicking in 0.7. So it turns out that B1 plus B2 always have to be 180 degrees, which means that B2 is 180 minus, I guess this is approximate, 45.58 degrees, which is 134, I don't want to run into my room here, so let's just go right here, 134.42 degrees approximately. So those are the two possible angles that law of sines could find for us. Okay, so in general, what's this one? This one, we have to be sort of specific, so I'm going to give you a little bit of extra information. This is definitely A bigger than H, so if H is smaller than A, but we also want to make sure that A is, let me think about this. What do we have? Smaller than B. If A gets, this is B right here, if A gets bigger than B, that actually forces the last possibility down here. If A is bigger than B, it has to stick out this direction. If it tried to stick back in, it would turn it inside out. So if H is less than A is less than B, we conclude that there are two triangles. Okay, so last one, and it's not a weird one. That was the weird one. So the no triangles and the two triangles are our weird ones. The last one is what we were just talking about. If the opposite side is longer than that adjacent side, it has to stick out this direction. So it's definitely looking like we only have one triangle. And our law of sines will say that sine of 30 over 1.3 should equal sine of B over 1. So this is 1/2 over 1.3. And then we'll take the inverse sine of that, which means inverse sine of 0.5 over 1.3 is 22.62 degrees. Okay, so if the opposite side is longer than that adjacent side, so this is side A is bigger than side B, or even equal to, we can throw the equal to in there, we conclude nothing too exciting. This is one triangle again. There is one triangle. Okay, so those are the 4 possibilities. 2 of them mean one triangle, but one of them is 2 possible triangles and one of them is no triangle. All right, thanks for watching.